So we're going to continue our discussion on diffraction by looking at a diffraction gradient. So what that is, we have, we considered like a single slit, either rectangular or circular, then a double slit experiment. Diffraction grading is very similar, except we have a barrier with a lot of slits in it. So we shine light, and so these are very narrow slits. So basically we consider light coming from one of these slits to be a point source. So we have all these point sources of light, and they're going to meet on the screen and produce a diffraction pattern. I'm going to hold up a picture from the book showing what it would look like. So we've got two pictures. The one on top is a diffraction grating, this one. And the one below it, this is for the double slit. So pretty similar, except the double slit is much wider. These are narrower, but a very similar effect. And what we want to do is we want to find out where the maxima would occur. There's a minimum in between each one. So we want to find out where let's define an angle. Let's say this is the first maximum here would occur at an angle theta. And so let's draw, I'm not going to draw the full lines, because again, just for the drawing, the sake of the drawing, this is not exactly to scale. Typically the width of these slits is very narrow, and they're extremely close together. The book mentions, this is, as far as I know, kind of a high number, but you can have up to 40,000 slits per centimeter. Usually it would be, like a couple hundred per centimeter, but they can make diffraction gratings. So like 1 centimeter, they'd have 40,000 lines, 40,000 slits. So again, this is not to scale. So again, these two rays are going to meet up on the screen, but they're very close to being parallel. And so what I'm going to say is the first maximum is going to occur when the path length difference, you're going to draw, so we have to consider light coming from all of these sources. And again, I draw them all parallel. It looks like they're going to hit on the screen at different points. But picture them, slightly angled upwards, so that, if the screen is far enough away, they're all going to meet at the same point. And so if we look at these two adjacent slits, what I'm going to say is that the path length difference to get a maximum should be lambda. So that would be lambda. So again, like from, when I drew this triangle here, so like the distance from here to the screen is the same as the distance from here to that same point on the screen. So the path length difference is lambda. And then we clearly remember delta equals 1 times lambda. That's constructive interference. If you're just considering two sources. I'll write that down here. This equation here only applies if you have two sources. So really be for just two sources of waves, whether light or sound. Okay, here we clearly have more than two. But what I'm saying is if the path length difference between two adjacent slits is lambda, then we'll have constructive interference. So we have to actually show why that is the case. So let's extend this triangle here. So this is lambda, and we have this big triangle here, where we have, these are just lines. They're just two lines. So basically all these triangles have the same angle here, theta. So and they're equally spaced, so this distance is the same as that distance. So if you look at this triangle here, these are all right triangles. These are the right angles. So if you look at, like this little triangle and this next bigger one, the bigger triangle, the distance is twice the little one for the hypotenuse. So the opposite side should be twice. So this would be 2 lambda. Similarly, this one is 3 lambda. So the first one is going to travel a certain distance going from this slit to the screen. Going through the next slit, it's going to have to travel through an extra path length. So yeah, let's just say we'll draw the first slit here. So it's going to go like this, and it's going to continue on until it hits the screen. The second one is farther away. So we're saying if one starts here, the next one is going to start back a distance equal to 1 wavelength. So it's going to travel through an extra distance. I should use a different color for this one. So this one travels through this extra distance. But you can see that it'll just overlap now. So these two will occur with the same phase when they eventually reach the screen. And then this next one goes, this one was lambda. So this next one starts back 2 lambda. So it'll just go through another cycle and then follow the same pattern. And so, again, you can always add a wavelength to without changing the phase. Okay, so the condition for our first maximum we have, so let's say D is the separation between the 2 adjacent slits. Then what we have is sine of theta equals lambda over D. So just from looking at the triangle. Okay, now what about the second maximum? Well, we would do the same thing, but we increase the angle so that the extra path length between these adjacent slits would be 2 lambda. Because then the next one would be 4 lambda, and the next one 6 lambda. It'd be like the exact same argument, just with a different angle. So, like the next time this would happen is if we went through this path length difference between the adjacent slits was 2 lambda. And so we could put a 2 in front, and that would give us another maximum. Or we could put a 3 or 4. In general, for diffraction grading, what we have is sine of theta is m lambda over d, where m is an integer, just like we used it that way before. And so, that's the basics of this diffraction pattern. Now, one thing that's interesting about a diffraction pattern is what happens if you shine white light on it. And remember, we have a lambda in the formula. So, like, the maximum would occur. We could solve for theta. D is fixed. So let's say we look at the first maximum, m equals 1. Sine of theta is lambda over d. Well, if we shine white light, which is a combination of colors, they're going to find that maximum at different angles. And so this kind of it does effectively what a prism does. If you shine light through a prism, it separates the colors. Diffraction grading does the exact same thing. There's also a picture of that in the book. So we shine, it says sunlight, but any, like a light bulb would work fine too. So again, it separates you get this rainbow effect with the diffraction grading as well. And these are used in a lot of experiments, probably more than prisms are. as far as separating light is concerned. Okay, so that's the basics of a diffraction grating. We could talk more about them. There's kind of like an inverse problem on this. We have, like here we have a screen that only lets light through at certain areas. Now, a related problem, what if we did the exact opposite? Instead of a screen, what if we just had little barriers that blocked light, but they could pass through everywhere else? And this is very similar to a diffraction grating. Now, why is this important? This is kind of what matter looks like in a lot of cases. Like, say you have a metal, just like, something on the periodic table, an element. If you could zoom in on an atomic level, you notice that the atoms that make up the metal form this nice structure where there's different types of structures. The simplest is kind of like, it's like a cubic structure where, if you picture just a bunch of cubes stacked up where the atoms would form on the corners. Sometimes you have a cubic structure with like an atom in the middle of the cube as well. You can have more complicated structures, but typically like these atoms are fixed in place. So if you shine light on this, the light's going to reflect off of these and appear much like a diffraction pattern. But just like diffraction, remember, in order to get diffraction to be significant, you have to look at, you have to use a wavelength of light comparable to the opening. So if you shine electromagnetic radiation at a metal, if you pick the right wavelength, so the wavelength is comparable to this separation between the atoms, they'll reflect off of the atoms in a diffraction pattern. And for metals, you would use X-rays. So it's called X-ray diffraction. And these were done in the 1920s. And that's our main way of learning, how atoms arrange themselves in something like a metal. Now, mathematically, it's very difficult to look at the pattern. Like, if you have a pattern, it's one thing to calculate what the reflection should look like, but this is kind of going backwards. You have to look at the reflection and determine what structure created it. That would be like a whole class by itself. So, just mentioning, one of the reasons why diffraction is so important is we can use it to learn a lot about the structure of matter. And so, using X-ray diffraction, you can learn about the spacing between atoms, and also like different types of ways they can arrange themselves. There's a lot of different names for it. But you can learn the precise structure and the spacing between them by using the right type of radiation. Okay, so I think that'll be it for diffraction. Let's do one problem and then move on. Let me pick a problem from the book. Here's one. Okay, the light shining on a diffraction grating. So, get something like that. Although these smudges are probably more visible than the lines themselves. But, okay. The light shining on a diffraction grating has a wavelength of 495 nanometers. It says in vacuum, but who cares? All right. The grating produces a second order bright fringe. So second order, that would mean m equals 2, whose position is defined by the angle. So if we just look at one slit here, this angle of 9.34 degrees. So how many lines per centimeter does the grating have? So that's what we want to figure out. So basically, we want to figure out the separation between the between two adjacent slits. That's what D is. So let's solve this for D. So we have D is equal to 2 lambda divided by sine of theta. So 2 lambda, 495 times 2, that would be 990 nanometers, divided by the sine of 9.34 degrees. Okay, so let's see what D is. 990 divided by a sine of 9.34. That'd be around 6,100 nanometers. Okay. Now, that's the separation between two adjacent slits in the diffraction gradient. So if we have, we want to know how many lines there are. So again, let's look at a diffraction grating this way. We've got these lines here, and they're separated by a distance d. So we can see that, let's say it has a length L. We can see the number of lines times d equals L. Now, there might be a little bit of an error in that assumption. Like if you were to have one line, for instance, you're off by a factor of 2, but we're going to have a lot of lines. So because, when you cut one line, you divide it into 2 pieces. There's always that one extra piece when you cut it. But again, when you have hundreds of lines or thousands, that's not going to make a difference. So we can say that N times D equals L. So in this case, L is 1 centimeter. So N, this is an L, kind of looks like an H, so I'll redraw it. So the number of lines would be 1 centimeter divided by 6,100 nanometers. So again, it's a length over a length. That's just a pure number. We can say there's 10 to the 9th nanometers in 1 meter, and there's 100 centimeters in a meter. So basically we have, this is nanometers. So 10 to the 9th nanometers, that's 1 meter, 100 centimeters is a meter. So we're just dividing, this is just 1 divided by 1. So we can do that. Everything cancels. So we have 10 to the 9th. Let's fix this a little bit. Let's say this is 6.1 times 10 to the 5th. So, 6.1 times 10 to the 3rd times 100. And then just to clean it up a little more, I'm going to say 10 times 10 to the 8th. Here, let's just do this. Okay, so I'll explain what I did here. Take 10 out of here. So 10 times 10 to the 8th divided by 6.1 times 10 to the 5th. So 10 over 6.1, and then we have 10 to the 8th over 10 to the 5th, which is 10 to the 3rd. So 10 over 6.1, it's about 1.64, and then times 1,000. So in a 1 centimeter diffraction grating, that's how many lines you would have. So spacing between them is very small. This would be 6.1 micrometers if you wanted to make the prefix a little bigger. But 1,640 roughly lines per centimeter. Okay, so pretty standard problem for diffraction gratings. But I'm glad we did this one because if you read it, it says the second order that would be m equals 2. So, yeah, I guess that'll be it for diffraction. And this was topic 56. We have one topic left to go, and that's 57 on thin films. So this is the second to last video that you have to watch.